Hi, Tor Lacey here, with a lecture about crustal deformation and mountain building. Most mountains are built along or near plate boundaries, such as the mountains in this photograph, which formed because the crust was squeezed and folded upwards by tectonic stresses. Here are the main learning objectives. Describe the relative movement of Earth's tectonic plates at each of the three types of plate boundaries. Utilize the fundamental principles of geology to determine the relative age of geologic events. Describe the relationship between stress, deformation, and structural features. Identify different faults and folds. Describe the interaction of rock bodies and structural features with Earth's surface. Interpret a geologic map. Describe how a folded or volcanic mountain can form. The geologically young mountains, those less than 100 million years old, are found along the active continental margins surrounding the Pacific Ocean and along an east-west trending region through southern Asia and Europe. How are mountains made? Mountain building involves deforming the crust or volcanic activity. Deforming the crust means changing the shape of a body of rock by bending and or breaking it. This happens when stresses are applied to rock, which typically happens along or near plate boundaries. Over time, stresses deform the crust into geologic structures, such as faults and folds. Through movement along faults and or the bending of rock underground, the crust can be pushed upwards to make mountains. Mountains are also made through volcanic activity. When magma is made that erupts on Earth's surface, building a volcanic mountain over time. Why does rock deform? Rocks deform because a stress is acting on them. Stresses are forces that push or pull or tear a body of rock. Earth scientists recognize three types of stresses: compressional stress, tensional stress, and shear stress. Compressional stress causes a body of rock to be squeezed. This mostly happens along convergent plate boundaries. Tensional stress pulls a body of rock apart in opposite directions. This would most be associated with divergent plate boundaries. Shear stress is a bit like tearing, where one body of rock is moved horizontally past another in opposite directions. This happens along transform boundaries or transform faults. So why all the stress? The rock making up Earth's crust is stressed out because of plate tectonics and the interaction of plates along plate boundaries. At divergent boundaries, two plates are moving away from one another, producing tensional stress. Along convergent plate boundaries, two plates are moving towards each other, and compressional stress is the result. Transform boundaries are places where two plates are sliding past one another. This action makes shear stress, though in reality it's more complicated, because all three stresses can exist at any of the three plate boundaries depending on different factors, such as the shape of the plate boundary or the direction of movement of the plates along the plate boundary. Stresses cause deformation of the crust, which changes its shape through bending or breaking. Bending and breaking change the structure or shape of the rock of the crust. Deformation changes the shape of the crust into structural features, which include folds, when a body of rock has been bent, or faults, when rock has been broken and shifted along a fault. How do we know if a body of rock has been bent or broken? We use a body of undeformed sedimentary rock as a baseline or starting point. This is a photograph of an outcrop of sedimentary rock. As you might recall, Steno's law of original horizontality states that sedimentary rock are made in nearly horizontal layers, known as strata. Considering this fact, we can use the horizontal strata of sedimentary rock as a baseline. Where we observe that sedimentary rock is no longer horizontal, we know that the crust has been subjected to deformation. Folds are always caused by compressional stress. Upward folded strata is called an anticline, while downward folded strata is called a syncline. This is an illustration of an anticline that has been partially eroded along Earth's surface. Here is an anticline and some more falcons. Here's a syncline behind a couple more falcons. This illustration outlines the progression of horizontal strata being deformed by compressional stress into an anticline and a syncline, followed by erosion and exposure of the limbs of the folded strata. Strata more resistant to erosion may stand out topographically as outcrops of rock. Brittle deformation makes faults and can be caused by any type of stress. There are two categories of faults, dip-slip and strike-slip. Dip-slip faults, also called vertical faults, are those where rock slides up or down along the dip of the fault surface. Normal faults are caused by tensional stress, while reverse faults are the result of compression. Strike-slip faults are either right lateral or left lateral, and both are caused by shear stress. Here's another Cerritos College falcon pointing out a small dip-slip fault. When naming vertical faults as either normal or reverse, the hanging wall and footwall sides of the fault must be considered. The hanging wall block is the block of rock resting on top of the fault plane, or the upper half of the fault. The footwall block is situated below the fault plane. Movement of the hanging wall, either up or down, will expose the fault surface, making a fault scarp. This photo shows a fault where the hanging wall moved downward along the fault surface. If the hanging wall moves downward along a dip-slip fault, it is called a normal fault. The hanging wall slides downward when tensional stress is acting on the crust. Here's a normal fault that moved very recently, producing an earthquake that you might have felt. If you were to visit the same spot 50 years from now, do you think the scarp would be as noticeable as it is in this photo? If the hanging wall moves upward along a dip-slip fault, it is called a reverse fault. The hanging wall slides upward when compressional stress is acting on the crust. This illustration shows compressional stress causing brittle deformation through movement along a reverse fault. Here's a photograph of a reverse fault. Notice how the arrows along the fault tell us which way the hanging wall and footwall are moving with respect to each other. Strike-slip faults involve horizontal or lateral movement along the strike or compass direction of the fault. They are the result of shear stress and are classified as right lateral or left lateral. Up to this point, we've been looking at structural features that are visible on Earth's surface. But what if a structural feature is below ground and out of sight? The only way to document the geologic structure is to make a geologic map. This is an example of a geologic map of Iceland. This is an example of a simplified geologic map of part of Wyoming. Like all geologic maps, this map was created using the orientation of the geologic units where they intersect the Earth's surface. The bands of color represent stratigraphic units or rock formations. Here is a block diagram of deformed rock. This perspective is useful because we can see the strata in cross-section and map view. Floating above the block diagram, we see how the structural features would be represented on a geologic map based on the pattern rock units make where they intersect Earth's surface. For example, the geologic map symbol indicates the orientation of the strata and how much it has been tilted. After the orientation of the strata has been measured, a geologic map can be constructed and the structure of the geology determined. In this case, the geologic map documents strata that has been folded into an anticline and a syncline. The product of crustal deformation can be a mountain, such as the folded mountain in this photograph. Mountains are also made through volcanism, or the process of making magma and volcanoes. Most of Earth's volcanoes are found along convergent or divergent plate boundaries, because these are the regions where magma is being made. Here, subduction is making magma, which rises through the crust to form a volcanic mountain, through repeated eruptions over time. This is Mount Fuji in Japan, which has been made through the process of subduction summarized in the previous slide. This ends this overview of crustal deformation and the making of mountains. Thank you for your attention.